Okay, you're good.
Okay, so obviously I gave you guys a little guys in here. Come on. In here. So I gave you guys, most of you, a little bit of a background. I know Shawn. We actually went to Math Science Center together in high school over at Andrews University, and so he's going to do a little intro, bio, and then allow you guys to ask questions. So I will let you go ahead.
Hello.
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 All right. Thanks, Julie. Yeah, welcome everybody to Houston, Texas, and particularly one of the mission control rooms here at the Johnson Space Center. I put together some slides. I didn't quite know you guys' background real well. So if they get boring, just let me know. If you have questions, just feel free to jump in whenever. I don't really usually do very formal presentations, so I'll kind of start with that once I figure out how to share the screen. All right, I think you guys can see my desktop now.
Yep.
All right. There we go. Full screen. All right, so I grew up in Niles, Michigan. That's pretty close to where you guys are. Hopefully you know where it is. It's not that tiny of a town, though it's pretty small. And so there's a picture of, I try to find the most embarrassing pictures of me I could find in this presentation. That usually makes it more exciting. That one is my grandpa trying to show me how the hard way to plow a field. We had a tractor, but he liked to show me how the hard way first before we ever did it the easy way. I graduated from Niles High School in '98. After that, I went to the University of Michigan, got a bachelor's degree in aerospace engineering. And then after that, I went to the University of Notre Dame. So the very question that everybody always asks is, which team do I root for when they play football? So that's why I have this nice little picture up here of them playing each other. And then at Notre Dame, I got a master's and PhD in aerospace and mechanical engineering. And also during that time, I got a pilot's license. So that's kind of why I threw that picture in there. All right, so kind of how I got to this job along the way. So right out of school, I first started working for Lockheed Martin. I don't know if you guys have heard that company. It's one of the bigger defense companies around the country in Valley Forge, Pennsylvania. That's just outside of Philadelphia. So I worked on a lot of defense projects there. I can only talk about that in front of generics. I think somebody asked that question if I've ever been sworn to secrecy. So those projects, the answer is definitely yes. However, once I transferred to NASA Johnson Space Center, most everything is pretty much out in the public. Only a few things related to security I can't talk about, but everything else. Oh, and the aliens, but we won't talk about those.
Aliens.
Yeah, and the aliens. So I am in the Flight Operations Directorate here at Johnson Space Center, and that also includes the astronauts, the flight controllers, as well as the engineers and developers for the Mission Control Center to keep it up and running. And that's the part I fit in, is the developers and engineers of Mission Control. So for my current position is kind of have two roles. One is the facility hardware architect. So that kind of oversees the technologies that go into Mission Control Centers. We have a data center, and also all the flight control rooms, like you see here, all the technologies that are involved in putting these rooms together. They're highly redundant, and they're fault tolerant. So if something were to go wrong, a lot of the systems can stay up and running. And then I'm also the lead for MCC. That's Mission Control. If I say any initials or acronyms you don't know, just yell out, because I'm so used to talking in that kind of language. So I'm also leading up the exploration development. So this is getting the Mission Control Centers ready for supporting the Orion missions, which is the NASA's human space flight replacement for the space shuttle to go into deep space, like the moon and beyond. And then Space Launch System, which is the rocket that will take Orion. I'll go into a little more details on that if you're interested in a bit. All right, so I thought I'd kind of go over a couple of the big projects I've worked on. I don't know, that might help bring up some questions that you might have, or just help understand my background a little bit. So after the space shuttle retired in around 2011, we kind of had this unique opportunity to upgrade the Mission Control Center. That's mainly because during shuttle, there was space station and shuttle always going on in the facility, so it was hard to go and upgrade stuff while all that activity was going on. But we did have to do the upgrade with International Space Station mission going 24/7. So that was one of the trickier parts of the upgrade. And so it was a 5-year project, and it just completed this year. We just finished the very last control room, which is called Flight Control Room 1. It's just down the hall from me. And that's where the International Space Station will be moving back to. They moved temporarily to a different room. So anyways, it was the largest modernization of the control center since it was first built for Apollo, starting the manned moon missions. So during this modernization, there was a lot of software and hardware updates. So on the software side, we redid pretty much all of the server side code, a lot of the user side code, and that's like all the displays and all the applications that the flight controllers interact with, and also the planners, the people that plan the missions and plan all of the things that are, all the experiments that go on board. The majority of the coding is done in C, C++, and Java. There are plenty of other languages, but those are by far the bulk of the code produced. And we probably have between 1 and 2 million lines of code across all of the systems in the MCC that we've developed custom, not including all the commercial applications. From the hardware design, we had to redo the network. We built a data center, which includes blade computing. That's kind of a picture over in the corner here. This is a blade center. So there's 14 of these little blades that fit in this chassis. And each of these blades themselves have 4 quad-core CPUs, 128 gigs of RAM. And so there's 14 of those stacked in each of these chassis. There's 2 chassis per rack, and we have a whole floor of racks. So it's quite a bit of computing power. And so all the flight controllers reach those usually by virtual machines. So on the desktops here in the MCC, well, you can't see it right now, but I'll give you a tour kind of the console in a bit. They have Windows workstations, and they use those for accessing their email and other kind of basic office items. However, when they want to do their flight control or issue commands to the space station or just look at any of the telemetry, they get on a virtual machine that's in our data center that runs Linux. And so all of the mission critical applications are run in Linux. So we also did a room design. This picture at the bottom isn't quite the best showing of it. Doesn't really look that much different, but that's what I get for trying to find this picture last night. And okay, so another project I worked on is called Exploration Flight Test 1. Better known to me as EFT1. I hardly ever look at the full name. But it flew on December 5th, 2014. And this was the first mission for the Orion spacecraft. And you can see here, this is kind of the configuration it was launched in. We used a Delta IV Heavy, which is a standard rocket that the United Space Alliance provides commercial companies to launch satellites into orbit. So we used that because the NASA rocket isn't ready yet until the next mission. And then it had the Orion crew module on top with no crew. The mission was pretty short. We launched from Kennedy, went around the Earth once, and then performed a burn maneuver to have a really high elliptical orbit here. And then when it returned back in off the coast of California, it was going about 20,000 miles an hour. And so we were trying to test the heat shield, since this is a completely new heat shield based on some of the technologies from Shuttle and Apollo with a lot of new hybrid materials. So that was one of the major objectives, was to test that heat shield. So that was that mission. Here's a picture. Not many people get to see the pictures of what it looks like when the spacecraft is being built. So this is a picture at Kennedy Space Center in a building called the ONC, and I cannot remember what that stands for. Operational, maybe in checkout building. And the green parts that you can see here are the main structural components, and then around it is all the flight computers, all the antennas, and all the various equipment. It's all kind of taped up, so it doesn't get debris and stuff in it. And on the bottom is the heat shield that's already been attached in this picture. So this is in a clean room in Florida. All right. This is where I was sitting for that mission in one of the other control rooms. So this mission took place right in the middle of our kind of upgrade, right in the middle of we were doing development for the new system, and we flew that mission on half the old stuff and half the new stuff. So from MCC's Mission Control Center perspective, we were kind of in this strange configuration. So that's why we had a bunch of guys on hand and ready to fix something if something broke within the control center itself. So that's that. And this is the flight control team. So this is the group that you would see on TV sitting in these, they're actually in this room, in these consoles, you know, looking very stoic and the stuff they usually do when they're on TV. But they were monitoring the system, sending commands, and watching, making sure all the mission objectives were met. And they let me stand in this picture, so I'm right back here. But they usually don't let us engineers sit in this picture. It's usually just the flight controllers. So I kind of snuck in there. All right, this is the next mission that I'm working on right now. It's called Exploration Mission 1. And this is again with Orion. However, this is getting more like it will be for crew. So this is the last mission before we put people on board. And so we're getting as much as we can ready to test everything before we put people. And this mission will be a lot longer. The other one was 4 hours. This one's going to be about 26 days. Again, we'll launch from Kennedy around the Earth once to check out, make sure everything is working. And then we'll fire the big rockets and do what's called the TLI, which is the Trans-Lunar Injection. And so a lot of this is already pre-programmed on the spacecraft. And so the flight controllers here are watching it. And if it's not nominal, then we can do quick corrections. Otherwise, the vehicle itself is autonomous and can actually perform this maneuver by itself. And then it'll take a 7-day trip out to the moon. And then it'll fire the engines again around the moon and go to this really deep space orbit around the moon. So this will take 6 days to go around the moon, and it'll go way out into deep space. And this is meant to simulate maybe going into catching an asteroid or doing some mission out farther from the moon itself. Then we'll swing back around the room, or around the moon, fire the engines again, and then return to the Earth in another 12 days, and then splash down off the coast of California. So that'll be a little more of an exciting mission, getting ready for adding people. And the really fun part about this mission is we get to, you can see here, connect to the Deep Space Network. So they have these really huge antennas in California, Madrid, and Australia. And they're usually used for like the Mars rovers or some of the probes that Jet Propulsion Lab has built, and they go way out into space. And the last time they were used for human space flight was during the Apollo mission. So we're pretty excited learning how they work again and connecting and trying to get data from the Deep Space Network. So we are so excited. We were doing high fives in front of the 70-meter dish there. All right, this is what the rocket and spacecraft will look like for EM1. This is a brand new rocket based on a lot of components from Shuttle. You can see the solid rocket boosters on the side. They're actually bigger than they were for Shuttle, but they're based on a similar design. The external tank, if you remember that from Shuttle, kind of fits in this region, but it's just a lot bigger. It's even bigger than the Saturn V. So it's meant to help support missions to the moon, missions to Mars eventually, and any other deep space missions, getting us away from kind of the low Earth operations we've done with the space station. All right, and on this side you can see Orion's on the front. It's attached to a service module with the solar arrays for extra power. And behind that is what's called the ICPS, which is the interim cryogenic propulsion stage. And that's the big boost that gets us from the Earth to the moon. And so once that gives us the boost towards the moon, then we can jettison it and get rid of it. Just for scale, this is how big the capsule is. There's 4 people inside. So that's me sitting on the side. And then I guess I should use a pointer. You can't see me pointing. And then on this side, this is what it looks like for the control interface. So this is where the astronauts would sit. And the displays are here up top. And they have lots of switches, and it is actually a screen display, so it's more of like a glass cockpit feel with just actual physical buttons around the outside. So during launch, it's very shaky, and there's a lot of movement in the vehicle, and the astronauts are feeling a lot of pressure on them. And so physical switches work a lot better in those situations, so that's why there's physical switches are all around the outside. But then when you're on orbit, it's a lot easier, and you can do a lot more functions with more of a a electronic screen. So it's kind of hybrid. Well, let's see. Other projects I've worked on. I think you guys have kind of been introduced to this. JSat Track is it's an open source Java application I started. So I originally started developing it when I was out in Pennsylvania, kind of on the off hours. There's a couple companies that sell a satellite tracking tool like this, and I guess basically what it lets you do is bring in existing satellites or design your own satellite maneuvers, and then just look at where they can see on the Earth and look at their coverage and when they pass over certain locations, both in 2D and 3D. And so there are commercial companies that sell like much more complex programs than this, but they have this basic components too, which is mainly what people need for doing basic analysis. And they sell it for like really expensive, usually like $100,000 a license, which is kind of outrageous for anybody else that wanted to use it. So I thought, well, hey, if I just start putting together something simple, people might find that useful and can use for the hobby kind of use. But it turned into a fairly big project over the years. Lots of people have kind of had suggestions and additions, and I just kind of worked on it slowly over time. So yeah, all the source code for it is completely freely available, and I can pull it up later if you really want to see it in action. But that's what that is. A few years ago, I also started up my own company called Gano Technologies, and the majority of the things from that is just developing mobile apps. Nothing really exciting. There's a hot air balloon pilot flight tracker, so that allows hot air balloons. My dad's a hot air balloon pilot, and so it allows them to track in 3D their flights and then kind of analyze them afterwards or share them with customers that go on flights, and then has a log book and everything integrated into it, and then a few other things like chess puzzles and some board games. But it's kind of a fun thing to do. And then also a hobby, woodworking is one of my hobbies. I like to, you can see there's some tops and some bowls, and there's a little robot I built. It's kind of a fun, creative outlet. And okay, control room, console video tour. If you guys are interested, let's see, I'll switch back out of screen sharing. Yeah, I figure out how to stop the screen share. All right, there we go. See how well this works. All right. I don't know how well you guys can see. These are the kind of the consoles in the control room. They're pretty much the same in all the rooms. On the sides, there's this key set that all of the flight controllers, when they log onto, this is where they listen to the different loops. So they have all this audio going into their ear they have a bunch of support engineers that sit in the back rooms that are helping them out. And so they can pull up loops and listen to what their conversations, talk on those conversations. They can have kind of communications loops with the flight director, that's the console I'm sitting at now. If you can see the name tag there. So then they could talk to them or other people across the country, maybe at the Deep Space Network or other places. Up on top, they have usually 3 computers. You can see 3 keyboards. They need at least 2 for shift handover because this is 24/7 operation. So one person will be working. So they do handover for about an hour time period. So they'll have 2 people working at the same time. And the third one is there for redundancy. And also we have a special network in case of we have a security issue where we have to isolate from the rest of the world. And so that's usually an addition there. But they have up to 8 monitors. You can see this one has 5, and they all can be controlled by 1 computer and 1 mouse. And then you can switch between the different keyboards and the different mice with all the inputs. And that allows a lot of flexibility on them bringing up displays. Let's see what else. Underneath, they have foot pedals, and that allows them to just, it's kind of like push to talk, like walkie-talkies when they're talking to other people. I can't see, that's too dark, huh? And then, so what other exciting parts are in there? They're really, all there are is pretty much glorified computer desks. But they have a lot of cable management inside, and then up front we have big screens, kind of like the hallmark of mission control. They usually have a map on one side where it shows all of where all the spacecraft are and what they're up to, just for situational awareness. And on this side, I kind of have a welcome to you guys up right now, but generally it's caution and warning. So if there's big issues that are going on, you'll see big red lines popping up here, so everybody can kind of pay attention to those failures that are happening. And then up top, there's, you probably can't see the real detail, but there's usually a lot of clocks going on or other just situational awareness things that the flight controllers look at periodically. So if you have specific questions, I can definitely go over them when we get to Q&A section, which is coming up soon here. Actually, that's my last slide. So yeah, so we can now do, if you guys have, I have a list of all the questions you submitted, so I can go through some of those, or unless you have new questions now, I can field those. It's kind of up to you. So jump in.
What version of Linux do you guys use?
We use Red Hat Linux. It's the latest. Actually, I think we're one behind. 1 point rev behind now. It's a little bit customized, but it's essentially right off the shelf Red Hat Linux.
You guys use Windows on a lot of the computers in mission control?
I think the question was if we use a lot of Windows in mission control itself.
Yeah.
And the answer is yes. On the desktop, they're all Windows. There's a few exceptions. The robotics console has a Linux workstation, and so does the biomedical engineer. And that's just because they have high-end graphics that work. The program they use uses Linux. But they only use the Windows essentially just to interact in kind of like the office standpoint. All of the actual applications that control the spacecraft are Linux on virtual machines in the control center. They just remote into them from the Windows machine.
Just so you guys know, the mic is a little quiet. You might have to either speak more loudly or get closer. They would actually.
Yes.
Are people working in mission control all the time, or is it just when there's a project?
Oh, for me?
Speak louder, a lot louder.
I meant, are there any people working in like mission control right now, or is it just when projects are occurring?
Oh, okay. Yeah. So right now we have 3 big mission control rooms. This one's called the blue flight control room. There's a white flight control room, which right now has ISSs in there, and they're in there all day long, 24/7. There's always some flight controllers watching over the crew and the systems on board. And this one right now is mainly used for training. So they'll come in here and train for, not quite yet the Orion missions, but there's a Boeing commercial crew missions that are going on. So they're training in here. Actually, right after this, I'm getting kicked out and they're coming in to do training. So it's kind of some rooms are always used and some other rooms are just used sporadically. Good question. So while we're waiting for other questions, I can go through the ones you guys sent. Let's see. The first one on the list is what level of programming do you have, from Anthony? I'm guessing like how much background of actual programming I have. I'm an aerospace engineering major, but I did take a lot of computer science classes, and my graduate work had to do a lot of programming. So I took quite a few. All the introduction, and then a lot of it was just kind of self-taught along the way, since they don't usually expect aerospace people to know how to program. But I found it very useful, and actually probably NASA has more computer programmers than they do rocket scientists, because so much, as like I mentioned, the mission is all mostly automated, and there's a lot of code that goes into even making the control center work and even the spacecraft. So. Another was, what's my favorite programming language? That would have to be either Java or the C variants. Those are the ones I use the most. What programming language do you guys use in your class?
We use Java.
Java.
Java through Dr. Java.
Oh, okay. So that's a good, yeah, and that kind of syntax carries over to pretty much all the other languages. So it's a good one to learn. And like, so what kind of fundamentals did you have to learn? I think that's kind of went along with the first question. It's probably the same kind of start you guys had, the basic programming, all the syntax, learning and just understanding logic. Then after that, it's learning more about systems and how you apply those code things for me for the aerospace side, and then just learning more about storage systems and network systems, and then how the programs interact with other systems. So that's kind of the fundamentals. Let's see, the other one is what level of education is required for your job? So probably the bachelor's in some engineering field is required. Graduate work helps kind of accelerate where you kind of fall in line, to help make up the leadership chain. So that's, but really bachelor's in engineering is all that's sufficient. Beyond that is just kind of how you feel. For me, I loved school, so I stayed in school, as you can see, a long time. I didn't really want to get a real job, so I eventually got out.
How has your job changed as commercial space flights become more common?
So that's kind of, I think a lot of people perceive that as kind of a negative thing of taking away from NASA. And from my standpoint I think it's a great thing. Now we can, so right now, up to this point, we've been very focused on ISS and kind of low Earth orbit exploration. And with commercial crew coming along, they're going to kind of take over the reins for going to that low Earth orbit, resupplying the space station and kind of getting some of that more stuff that we've done in the past. I mean, not that it's not risky, but that it relieves us to go and allow us to go explore these big Orion missions where we go to the moon, to Mars, and maybe asteroids and other big exploration topics. So it's kind of somewhat of a relief in that sense. But it's also you get a little bit of jealousness too, so seeing SpaceX doing these new things and building new rockets along the way that's a little bit faster. So it's a mix, but it's definitely exciting. It makes the kind of internal space race between commercial companies and NASA, but we're all working together. It's a good question.
Something just came to my mind. It's have you ever heard of like white knight hackers or like anything, people who like break down like or hired by companies like Google, for example, have people that they use to try and break into their own systems and see the flaws in their system. Do you have anyone like that ever do that for your company?
Yes, like penetration tests. I guess that's kind of what we call them. Yeah. Yes, we do. So so part of the government, there is some agencies, I guess, in the government that then they loan out their expertise, and they come about maybe once or twice a year, sometimes unexpected, sometimes expected, and they'll go through and try to break into all of our systems and then give us a big report of what they got into, what they didn't get into. And so that definitely is something that's become a huge thing within the control center. When we've modernized it, we've allowed a little more access out to the flight controllers. Maybe even sometimes they can get to some of the data from their house. And so we've been really, really worried about kind of attacks like that. So definitely. Let's see. I'll just fill in with the other questions until you guys think of other ones. What is most difficult about your job? So the thing that's most difficult in my job is probably dealing with people. It's mainly because as things change, people change their minds, change their requirements, and then just there's a lot of people involved. And so not that necessarily they're hard to work with, it's just there's a lot of people to work with in different locations, have different requirements, and they're really trying to do different things. And so trying to get everybody on the same page, working towards a common goal and with this kind of same set of expectations, that's generally the toughest part about it. The engineering, after you kind of have a rhythm down and you're kind of setting that. It's definitely the challenge is dealing with the big teams and the people. And it's not negative, it's just kind of how it is.
You talked about redundant systems a little bit.
Yeah.
Code redundancies you build in.
Oh, okay. So it's for the control center. It's essentially everything, every step of the way from the flight controller to the spacecraft when they have to send a command is completely redundant. So we have 2 power systems under the floor that connect up into the consoles, and they have the computers are all fed by different power sources. We have a diesel generator on site to kick over in case we lose power from the commercial providers. Let's see, what else? Up in our data center, I show you that kind of the blade framework, and by having running virtual machines in the back end, if one of them were to go down, if there's a fire on one side of the room, for instance, we have a software called vMotion, which essentially can move all of the virtual machines over to different computers in real time without the flight controller actually even noticing. So within one or 2 seconds, it can transfer their entire session over to other computers, and to keep it running and to keep things up. And then we have 2 lines that go out to White Sands, which is the ground station that sends the actual radio signal up to the space station. We have 2 lines that go out, and they're diversely routed, so they don't even take the same geographic path, because in case somebody has a backhoe and they dig up something on accident, which does happen more often than you would think. Somewhere in Oklahoma, somebody was working on some project, and they dug up a line. So that's why we have 2 of those routed to White Sands. So we really try to do one fault tolerant all the way from the person to the spacecraft. Which at times may be overkill, but it definitely comes in handy, because operating 24/7, everything goes wrong that you can't even expect.
What's your bandwidth look like day to day? Like just data going back and forth from.
Yeah. So our big one is the International Space Station. We get both telemetry, which is over 100,000 parameters a second. So. And then we have video coming down, 4 streams of video. With the new upgrades, I think we're pushing like 300 megabits a second from the space station generally. So and then we have to archive it and store it and to display all that data as quickly as possible to the flight controllers. So it's definitely that's the big challenge, is dealing with all that data.
How did you come to work for NASA? Like, was it your goal, or did it just, I don't know, did they recruit you?
No, it was definitely my goal. The human spaceflight has been kind of a passion of mine since I was in school, and so yeah. Then I went to Pennsylvania working with Lockheed Martin, but I was doing all I could to try to get a position within NASA. And so there's a couple projects that came up there that had to do with some NASA or kind of unmanned spacecraft projects that they're working on. So I tried to get on those projects, and once I got in there, I met some people here at NASA and sort of just worked my way over here slowly. So yeah, it was definitely intentional.
From a student standpoint, like your education was from Michigan and from Notre Dame.
Yeah.
For kind of considering where they want to go to school, like what are some of the other schools that your coworkers went to that would kind of have a pipeline into NASA if that was their career ambition?
Oh, okay, yeah. So yeah, NASA they're at the career fairs of a lot of big universities across the country. There's a lot of people from Texas here just because they live in Texas. We're in Houston. But other than that, there's Purdue is another big draw. Penn State itself. I know some people from Embry-Riddle, which is another aerospace company. They're more of the airplane side, though. It's a big scattering from. There's some out west. Stanford. You know, the one thing is I applied to MIT and didn't get in, but I have only seen like one person from MIT around here. I'm sure there's more, but I would expect. But so it pretty much any good school with a good engineering background or good engineering kind of reputation is sufficient. And then you can just keep applying. That's the main thing is keep applying, show a high level of interest. And that's probably my best advice on that. Good question. Anyone else?
Well, I'm wondering. So you said there's like the engineering side, and then there's like the people that kind of control the mission, or like are in charge of the mission controls. But
Yeah.
who are the people that are in charge of like the creation of like the ideas, like the mathematics, and scaling it, like doing all like the core work on big like Orion mission?
Oh, okay. Yeah. So the people that are building like the spacecraft itself, and
Yeah.
they're in the engineering. So I'm in the flight operations division. That's probably why you hear me talk about astronauts and flight controllers a lot. There's a whole other division that's the engineering division, and they're the ones doing like the structural analysis, the electrical analysis, and the thermal analysis on the vehicle itself, and designing the shape of the heat shield. So that's that division, and it is the same kind of thing. Background in engineering, a lot more mechanical, electrical, and thermal, and less computer science there. Though there is definitely some to do some of their big scale simulations. In our division, some of the flight controllers, when they're not on console, they're actually doing the trajectory analysis. So there's a lot of computations going on there as well. They're trying to calculate the best burn paths for spacecraft and the best attitudes to be at. So when you're facing the sun, you can get a lot of heat on one side, and then and on the back side it gets cold, and so you have to rotate that around. Otherwise, you get these thermal expansions and contractions that can cause problems within the structure. So it's definitely spread out a lot of the controllers. The controllers themselves are all engineers as well. They just go through a different training sequence. They're more trained to deal with the problems as they come up and tackle them real time, as opposed to designing the structure. And I do like the design side, and that's why I didn't chose the flight controller path, because I like to build things, and that's part of the building up of the control center has been a good project for that. But yeah, so there's definitely engineering side too. So yeah, I just kind of have not mentioned that. Good point. I should probably put that in my presentation in the future. This is my first one of these. So.
What language do you program for your application?
For like the ones that I have done.
Yeah, like your business.
Oh, business is because I do mobile apps. It's mainly Objective-C. That's what Apple's iOS uses. I've done a little bit of the Android Java-based stuff, but it's mostly the iOS Objective-C. Swift has come out of. I played with it a little bit, but I had so much of my code already in Objective-C, and I like to steal from my code, so it's kind of hard switching between the two.
How long do you spend on one program, like one particular app, or one thing for design for missions or such?
Okay, so yeah, in the mission, the programs, there's definitely a huge variation. There's really small programs that just monitor like CO2 levels on board, and they're maybe 100 to 1,000 lines that take maybe a month or so with testing. There's a lot of testing that goes on to make sure that it performs the way we want it to do, and so that's a good chunk of the time. And then there are applications that monitor the full electrical systems and thermal systems on board, and they model them to try to predict what's going to happen in the future. And those take like 8 people, 2 years of projects. So those are really big. So it's definitely a big range.
What is the most complex program you've ever written?
The most complex, it's probably that the JSAT track program's probably the most complex. I was looking through it last night because you guys had asked a couple questions about it. And it has a couple hundred files, and they're each, I don't know, there's 1,000 lines or so in them. Not all, most. I mean, some of it's comments and brackets and stuff, but it turned out pretty large.
More about the timeline for Orion.
What was that?
Can you speak more about the timeline for the Orion mission?
Oh, sure. So the next one is Exploration Mission 1, and that's without people, and that's going to launch in 2018. And then 2 to 3 years after that will be the Exploration Mission 2, which will have people, and that'll kind of run a similar mission around the moon and out in 2021. So we're on 2 to 3 year time increments, mainly because of just funding. NASA's not really, it doesn't have a high funding level at this point in time. But then after we get going, it should be missions on a yearly basis. So 21, 22, hopefully one mission a year.
I think someone brought this up in class the other day that people were testing like lying down for long periods of time. Is that because the capsule for Orion is not big enough to actually be moving around enough, or something, or like how is the capsule for Orion big enough to actually have movement, like so you don't get muscle atrophy or?
Yeah, so the Orion capsule is small, but the nice thing about being when you're on orbit is you're not confined to kind of the what we're you don't have to have a ground plane. You can kind of float around inside of it. So there's a decent amount of volume in there. I wouldn't want to stay in there for more than a month, and that's not really the plan. So if we go on like long-term missions, the plan is to dock to like a habitation module to go to Mars and somewhat, but for a couple weeks. So I guess the best way I can kind of describe it is sometimes if you're in a small bathroom and you feel like it's small, but if you ever look up and look at all the space that's up in the actual entire room, or even a closet, there's a lot more. If you could just float around in there and actually put computers and windows and those locations, you'd be surprised how much space there actually is in kind of those containers. And then you don't have the pressure on yourself. But those studies are generally of, hey, you're in tight quarters. They have them lying down, and that's mainly just so they don't use their muscles, and not because they need to be lying down specifically. So they just want to see what happens long durations of somebody not using their muscles. Because when you're in space, even though you're moving around and stuff, if you're just staying still and working on a computer, on the Earth, gravity is pushing you down, and so your muscles are always fighting that back up. But in space, you don't have that kind of force against you, and so all of your muscles tend to atrophy, just because they're used to a constant pressure. I don't know if that helps, but that answers the question or not.
Yeah, that did.
Yeah, I hear them asking for volunteers every once in a while. I'm like, no way would I volunteer for that, sitting on a bed for a month.
And then you get up and you realize, what have I done to myself?
Yeah, exactly.
So what project are you most proud to have worked on so far?
The one I'm probably most proud of is the EFT-1. Even though the mission control modernization was a huge project and it was exciting, the EFT-1 of getting ready to actually put people into space definitely was kind of goes back to when I was in high school, really wanting to be part of human space flights. So that was pretty exciting. It was really exciting to be here on mission day in the control rooms, even though I had to get up like super early in the morning. I thought today was early, but I had to get here like almost at 1 o'clock in the morning to support a full day of a mission. So, but that was a lot of fun.
Go to sleep.
So
Yeah.
by high school, you were really sure that this is what you wanted to do? That's
Yep. I wanted to be an astronaut, but this is close as I've gotten. I've applied 3 or 4 times. That'll be thousands of people. They only take, a dozen, so pretty low chances. But doing this stuff is pretty close.
About a year ago, they published the Apollo source on GitHub.
Yeah.
How much of that has been reworked, or are the foundations of it still usable today, or is it completely obsolete, or what's that transition like? Looking from Apollo to Orion, wanting to do similar work.
The math I think stays. I don't think we're using any of the code from the Apollo, even though there are some really funny comments that the Apollo coders put in there. Every once in a while you read lines and they talk about kind of funny stuff that's around here. The actual math and the basics of orbit trajectory definitely are still applied, but we don't use the same code. A lot of the shuttle code though still exists in some of the core functions of the control center and of the spacecraft. They've used some of it in kind of the guidance systems, but definitely Apollo has been kind of reworked since then. And they used a lot of 4chan and a lot of assembly cards, so they had these little punch. People tell me stories about punch cards and dropping them all over the place. So.
I think the bell's gonna ring in 1 to 2 minutes. So if you have extra questions, we can probably send them to you. I'm pretty excited to answer some. I'm sure people might have a lot of extra questions. That's okay, yeah?
Yeah. Feel free. Send me questions anytime.
Can you hold for a second while and then I just want to talk to you a little bit after the bell? Yeah.
Sure.
Okay. Thank you, everybody.
Everybody. Nice meeting you.
Can you read that up?